Welcome everyone to Managing Game State in Flutter, Part 1. My name is Craig Labenz, and I'm a developer relations engineer at Google, and I work on Flutter. And today we're here to talk about making games. And if I have one central thesis today, it's that app developers are game developers. And you might be thinking, really? Well, Flutter app developers are 2D game developers because Flutter uses Skia, a 2D rendering engine. Now, this is a 2D game, kind of. So am I saying that Firaxis should use Flutter to build Civilization 7? I am not. But for relatively simple 2D games, then I think our Flutter skills translate perfectly. And to dive into this a little bit more, let's think about what is a Flutter app in its simplest form. If you were to break down Flutter into the most simple pseudocode possible, I think it would basically look like this. There's a loop, and first it renders all of your widgets, and then it waits for you to call setState. And that await word there is important, because it means that Flutter is willing to kind of slow down when nothing is happening, and our users' battery lives thank us. So that's a Flutter app. Now, what's a game? Well, a game's simplest pseudocode looks pretty simple, or pretty similar. It's got a loop, and first it renders the state, and then it updates the state, processes any user inputs, allows all of the NPCs and any enemies on the screen to move or shoot or whatever. And a key difference, though, is that this game loop always wants to go at max velocity, because games generally assume something is happening, always. There's always a need to re-render. Even in Pong, one of the simplest games ever, that ball is always moving. So the assumption in game development is that more frames is always better. So is the difference just that in Flutter, your app is willing to slow down and save battery, but a game is actually just trying to max out the GPU? Maybe, but I think the difference is that we think of games as just being fun. Using a spreadsheet app or like a booking app or an e-commerce app, they're not fun in the way that Flappy Bird was fun. And I think that's actually basically the only difference between a certain type of game and the Flutter apps that we're used to building. I think once you start using a framework like Flutter or Unity or Unreal Engine, then all of the skills that we've acquired building normal apps translate perfectly to games. So yeah, I think app developers are game developers, which brings us to the question of what game are we building today? Well, Puff and I brainstormed a game that fit within the following constraints. One, we needed it to be easily multiplayer-ified. Two, it needed to have minimal server-side logic while still being server-side authoritative. And then three, we have to be able to build it in 1 hour. So what we dreamed up was this kind of multiplayer maze game. And all connected players to the game will be controlling the same game piece. So we've got a little bit of intended chaos. Good luck coordinating as you try to escape the maze. But let's now think about our to-dos. What do we need to get done to actually deliver this game to Puff so that he can make it a multiplayer game? Well, first, we need to choose our technology. Obviously, it'll be Flutter-based. Then we need to actually write some code to instantiate our game state. Next, we need to position the board on the screen. And there's actually some subtle complexity there. Then, in that space that we've positioned, we need to render the actual maze. Then we're going to need to make our game dynamic by listening to keyboard events. Once we start receiving those keyboard events, we can then update the position of the player indicator. Move the player around the maze. But not everyone will have a keyboard. People on a phone won't want to use virtual keyboard. So we're also going to add voice commands, so you can just shout at your phone or computer. and say up, up, left, 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 and escape the maze that way. And then we are going to pass the baton to Puff. So let's get into it. First, choose a technology. Now, the only real question here is, should we use Flame? If you're unfamiliar, Flame is a 2D game engine written in and for Flutter. And I checked out Flame. It's kind of always been on a list of things that I wanted to spend some time learning. But after studying it a little bit, it has a proper game loop. It has a ton of useful mechanics like collision detection for different sprites. But we're just walking out of a maze. So I actually thought that our game is too simple for Flame. But if I was making anything interesting, Flappy Bird on up, then I would use Flame. But we're just going to use widgets. We're just going to be totally vanilla Flutter. Okay, one down. Now it's time to start instantiating our game state. And the first question that I think we have to ask ourselves is whether or not game state management is intrinsically different from like normal state management. But to answer that question, let's look at some state management and kind of see what it does. So I think that there are 3 core jobs that any good state management solution has to do. And the first one is to establish the initial state. You got to know, what is the first screen that I need to run? What is the level before the player has done anything? Then we need to expose some methods for other code to update the state. And lastly, we need to expose a way for the state management, or the state management has to have a way to re-render after one of those state updates. In Flutter, obviously, that always routes through setState, which is what tells the framework to re-render the widgets. So here's some pseudocode that uses Riverpod, which I don't think many of us would think of as a state management solution for games, but maybe. Let's see if we can spot where each of the 3 core responsibilities of a state management solution are fulfilled. So step 1, this is pretty straightforward. The initialization happens in the constructor. We expected that. Now step 2, all those methods to update the state, well, they happen anywhere you just have a method. So that one's actually also kind of a freebie. And then in Riverpod, to re-update, you reassign the state variable. This is kind of a magic variable. It gets set in that constructor supercall. And anytime you reassign to that variable, then Riverpod says, oh, wait, time to redraw the app. So Riverpod does the 3 things, and we're going to see if these 3 things are enough to make a game. Now, quickly though, tucked up in the upper right, we see a reference to this maze state class. And I want to quickly peek at that because it's pretty core to what we're going to be building. So here's the maze state class skeleton, and you can see that I'm using freezed because freezed helps me generate a lot of very useful boilerplate and allows me to just think about which attributes my maze state class has. And those attributes are, first, the player location. We have to know where they are. The coordinates class you see there, by the way, that is, it has 2 attributes. They're both integers, x and y. That's all the class is. So we need to know the coordinates of the player location. We also need to know the coordinates of the target location. How do we win? What square is the victory condition? By the way, the x and y in coordinates, those are like game board locations, not pixels. They're just pure game logic. No display considerations yet. So we need to know where the player is and how do you win. We also need 2 integers for the size of our maze. How many rows, how many columns? We've committed ourselves to a rectangular shape. How many players are connected? We know that Puff is going to turn this into an MMO before long. So we'll get our state ready to start rendering some of the things that he'll care about. The last command as well. This one's interesting because one day you're not going to be playing the game by yourself. So the last command might not have been your command. So we want to render that as well. The number of moves in total. This is pretty standard to keep score. Then a start time so that we can have a high drama countdown and say 3, 2, 1, go! And everyone will issue the same command and the player will dart across the maze. And lastly, arguably most importantly, we need the list of coordinates that represents the wall locations. Where can you not walk? Where will you bump into things? Now in the middle, we've got this move command class kind of sneaking by. So I want to peek at that one as well. And the move command class for us is actually just kind of a fancy enum. You can really think of it that way. But the fanciness comes from freezed, again, because freezed offers us this map method, and it's extremely high value. And just kind of keep that in the back of your mind. We're going to come back to that map method. Okay, so our maze state class is looking ready. And we can zoom all the way back out to our manager. But that maze state.initial method didn't seem to exist. We were just looking at the class. There was no initial method. So the first question, as we turn this pseudocode into real code, is, remember that wall locations variable, that list of coordinates. The first question in getting the initial state of our game is just answering the question, how are we going to get that information into memory in our application? And to store the level, to store the nature of a level, the state of a level in the beginning, for simple kind of grid-based games, I like to use just a plain text representation. Every character, means a certain thing. There's only a certain set of valid characters. And your code can very easily consume this list of strings. And critically, it's very easy to visualize and edit ourselves. And we have a very easy turnaround from kind of the primitive definition of a level to seeing it rendered in our app. So this is a plain text representation of a level, of a maze in our game. So we go back to the maze manager and we can replace that old fake initial method with a real method, and it's called parse maze. So what this method does is sets up a couple variables that are the things that we care about, and then it loops over the maze and fills up those variables. So now we know where all the walls are, we know the player location and the target location. And that code is actually very trivial, but takes up a lot of space. So I've just kind of omitted it here. It's all on GitHub. The next step that we have to do is actually return that initial state. That's contractually required of us by Riverpod, and pretty much every state management solution has settled on this requirement. Block, all the other ones. You owe your manager class, or it's called a block in block. Here we're using a state notifier. You always owe that an initial state value right away. So we return that here, and that's that. Now there's one more piece of Riverpod specific maneuvering that we're doing here. We create this provider object, and our widgets can use this to access the maze manager. And it's safe to put it here away from the build context because there's nothing that we're doing here that actually needs the build context, because we have no display information here. So we don't need to know the size of the operating system or any of those things. This is just kind of pure ivory tower game state that we're working on. Okay, so we've now instantiated that game state, and it's time to position the game board. And we had to instantiate the game state first because that told us how big the board is, and critically, its shape. So if the aspect ratios of the surrounding window and our maze are the same, then laying it out is pretty straightforward. Right here, the red box represents where the maze will go, and how we would position it, we give it a little padding, makes total sense. But what if this same maze is rendered on a phone with a totally different aspect ratio? Then we have some questions to answer. And what if it's in a browser and it starts in this shape, but then the user just picks up the corner and drags it, and the aspect ratio changes on us on the fly? We don't want to maintain our old layout because it would be really small in this one, in this aspect ratio. So the rules that I came up with for this involve, we're going to ultimately use a stack to render our maze in the middle here, but we're going to have a 10% buffer on the most constrained side. And we don't know what side that is. We're going to have to calculate it. It might change on the fly. We're going to have a 10% buffer on the most constrained side, which creates an unknown amount of padding on the other side. And again, we have to calculate which side is which. So how do we handle this? Well, if you've made some fun layouts in Flutter before, you've probably used the layout builder. So we're going to wrap the whole thing in a layout builder. And here's some pseudocode for what that kind of looks like. We can see we've got that padding widget there at the bottom, but the maze padding variable is key. That's what we have to figure out. So let's look at those calculations. Now we can see here that we're getting the max ideal width and height of each individual square. And it's each individual square because we're dividing by the number of columns and rows. So here we say, hey, game board, each square, how big would you be if you had to fit in 80% of the screen real estate? And that padding on constrained side variable, by the way, that's basically our 10%. And just allow it to be configurable. So we find out how big each square would be in either dimension, and then we just take the minimum of that for the most constrained side, and that's how big each square will be in the game. And this variable is all important. We are going to use this again and again as we lay out our game. The square size variable, we have to know this. Moving on, we can use that variable with the game size to calculate the actual dimensions of the maze. And then we combine that with the constraints provided by the layout builder, and we finally arrive at our maze padding. So returning to the previous code, we have our maze padding now, and we can position everything in the middle. And I've got a video here that shows us how this behaves. So let's play the video. And as we're dragging the window around, we see that the maze is trying to be as big as it can while always honoring a 10% buffer in the most constrained dimension, whichever one that is. Now, you might be wondering, is there a widget for this? And the answer is like, kind of. It takes a few widgets. So if we imagine starting with an aspect ratio widget and using the dimensions of our board, then we could ensure that we would render something that was the correct shape. So this red square is going to allow every square in the board to have the same height and width, which is what we want. But of course, it's too big. So we've lost our 10% padding. We're not centered. Everything else is broken. So we'll wrap that aspect ratio in a fractionally sized box. And here we say, hey, if height is the most constrained factor, then you get 80% of the height. If width is the most constrained factor, then you get 80% of the width. Okay, that's pretty cool. And that 80%, by the way, that is, again, I was just shortening the 10%, so it would fit on the slide. But you still use the variable. Okay, so this gives us the correct size and shape, but the wrong position. We're not centered. Of course, centering things is the easiest task a Flutter developer will ever do. We wrap our thing in a center widget, and we're right back where we started. This is a perfectly positioned game board. Now, we might have thought that was easier, but we critically must still have that square size variable. So we actually can't skip all of those calculations anyway. So either way forward. Now, this layout structure that we just went through felt different, right? But it was the same old widgets. So kind of game layouts, they can feel very different than kind of normal app layouts, but same old widgets. Okay, it's actually time to render the maze now. So we said we're going to put everything in a stack, and this is going to show our entire game. Everything that was the red square is going to be this stack. So first thing that we want to do is create a list of widgets for our horizontal bars and our vertical bars. And these are just simple containers. You can see here, horizontal bars, they're going to stretch right to left across the screen. So they're 1 pixel tall. And then the vertical bars are going to stretch top to bottom across the game board. And so they're 1 pixel wide. And we take those just plain widgets and we throw them in a column and a row respectively in our stack. And suddenly we're rendering a grid. And this is starting to look useful. This could be a game. But we don't have a player indicator yet. So let's add that. This code will nicely draw just a simple circle. So if we start in the middle, we see this container. This is actually what draws the circle. It has a sufficient border radius and a fill color. So that's a circle. But we're in a stack. So we know that we're going to want to use a position widget to put it somewhere. But it would actually kind of be nice if the player kind of moves to the next square instead of teleporting. So we use an animated positioned widget to cheaply achieve that effect. And lastly, we need to position it correctly. And we can see here we use square size to translate game coordinates into pixel coordinates for the screen. So we go back to our stack, we add that, and now we're rendering the player indicator at coordinates 3, 1 currently. We're 0 indexed because naturally. Okay, now we need walls. So our maze state had that list of coordinates, the wall locations, and we can see now that we're just kind of like building this all up with vanilla widgets. So we're going to loop over the maze state.wall locations, and we're going to build a list of just containers is what we've got in the middle there. And again, we use that magic square size variable that we all importantly calculated to translate the location of each wall into where it should be in the stack. We return to the stack when we kind of plop that list of positioned containers, the wall blocks variable, right into our stack. And oh man, starting to look like a game. All right, next. We need to start listening to keyboard events because right now this is an extremely static maze. Okay, there's 2 different ways that we can do this, and we're ultimately going to do it in both ways. The first way here, we're starting work on what I like to call a non-UI widget. And this widget has functionality in our app other than impacting the layout. So visually, there will be no change when we add this widget. But it's called the Move Command Keyboard Listener. So you can kind of imagine what it's going to do. And one of the most important things it does is accept this function in the middle, the send command function. And this needs to ultimately route all the way back to our maze manager, which is actually keeping up with the game state. So we hope that any move commands we shove into this method will find their way back to that. But let's move on to the state class for this stateful widget, because that's where the good parts are. All right, in our knit and dispose, we see that we're registering a handler with this hardware keyboard thing. And if you've not heard of it, Flutter provides this to give you access to every single keyboard event that the Flutter engine receives. And this is independent of whether there's an input that might have focus or any other shenanigans going on. You will get every key press. So we register, and then later we dispose this onKey event method. So what does onKey event do? Well, first thing is it discards all key up events so that when the user presses a key, we only process it once. Turns out that's important. Then we check against all of the different arrow keys. We're only showing 1 here, but we check against each arrow key, and if it's up, down, left, or right, then we send the associated command through that method that we were passed. And then the build method, the last part of this widget, I promised you a non-UI widget, so this does nothing. It just passes through its child. Now, you might be wondering, what does the use of one of these non-UI widgets look like? Well, kind of just like any other widget. We can see here at the top, it's our Move Command Keyboard Listener. And the usefulness of these is that it scopes certain behavior to a page. And so we just wrap it around the scaffold where we want to be listening to keyboard events thusly, and we are only doing it on that page. We've got a scaffold with our maze there in the middle. And then this send command that we owe to the Move Command Keyboard Listener, that parameter, we use Riverpod's magic ref object to go grab the notifier and then access its method, and we're passing it through as a tear off. Okay, so our UI is now reporting events, but still no one is listening because that send method doesn't actually exist yet. So let's write it. So we're back in the maze manager class, and we need something that gets these move command methods. So the first thing that this does, if we remember, the move command class was generated by freeze. And I was very excited about that because I said it gives us this map method. And what that does is take a callback for each type that the thing could be. Remember, I described it as a kind of fancy enum. So enums have a certain amount of flavors. Well, our move command has a certain amount of flavors, up, down, left, right. And the map method says, I don't know which one I am. I'm just a move command. So give me a callback for each one that I could be, and I'll call the correct one. Now, and this is exciting because these are required parameters. So maybe one day we're going to add a back command, and it just undoes the previous one. It'd be very easy to forget to go to all the places where we have code like this and add a handler for that back command. But freeze will add a required parameter. So we'll get a linting error if we don't. It'll make it impossible for us to add a new flavor to our enum, but forget to handle it. So what does this ultimately do? It translates the player's current location, kind of through the move command into their next location, where the player is going. Of course, unless they're trying to move out of bounds. Also, unless they're trying to move into a wall. If either of those things are happening, then we discard the player's move. But if neither of those things are happening, then we lean into Riverpod's, if you reassign the state variable, I will update contract by reassigning the state variable so it will update. And we just have the new player location. And that animated positioned widget, that's going to move the player there instead of teleporting it. And, and then we've got some other scorekeeping to do as the number of moves have gone up and all that. So we've got another video here. You can probably imagine what this looks like. It's the maze, but as I press arrow keys, the character starts to move around. All right. So next up, we just need to listen to voice commands because, again, that keyboard input pattern is not going to work for our mobile users. So, okay, we want speech to text. There's a package for that. Amazing. And it routes whatever audio it hears to the device's native speech recognition capacities, or capabilities. That's the word I wanted. So it's just going right to your browser or your phone. It's not like a Google ML thing or a bunch of Dart code or craziness like that. So before we talked about using this non-UI widget. Well, the other way that you can do this is to just have a dedicated class in your provider, in your state management apparatus. If this is in fact a non-UI thing, and speech, listening to speech, that's not really going to impact our UI directly. So we're going to use a dedicated Riverpod class. It's another state notifier. We've got speech state. We can imagine how that looks. The first thing that this does is instantiate the main helper class from the speech to text class. And then we also are going to require the send method, the same thing that our keyboard listener required, because this still has to route all the way back to the main maze manager. And then we need a way to turn the thing on. And ultimately, that gets us into on-speech result, which is some pseudocode. This line right here is really the pseudocode because it's kind of non-trivial to make sense and unravel the data that you get back from the speech-to-text library, but it's all on GitHub. Then we update our UI so that users can see what text is the plugin thinks it's hearing. And ultimately, we check those words for left, right, up, and down, and we send commands. And that puts us at a functioning maze escape game. And we just use normal state management, normal widgets, but we reapplied all of our kind of common Flutter knowledge to making not a typical app, but a game. And it's ready to be taken into the 21st century, the age of the internet, by Puff. So, Puff, take it away.